Hi friends, welcome to follow up. In this video, we are going to look at problem 1727, largest submatrix with rearrangements. So our strategy will be a combination of sorting and a flavor of dynamic programming. So we are going to first look at the problem digest, and then we look at the analysis or algorithm, and finally we code the algorithm. So here, we are given a binary matrix of sets m by n, and we are allowed to rearrange the columns of the matrix in any order. So we want to return the area of the largest submatrix within matrix, where every element of the submatrix is 1 after reordering the columns optimally. So here we have three examples. If you look at example 2, it's just one row. It's very special. But now if you put all the columns with ones in the beginning or at the end, so you're going to have 1, 1, 1. So the area is 3, right? So for the first example, so notice that for the first column, there are 2 ones consecutively. And for the second column, there's 1, 1 consecutively, which is in the middle. And while the last column, it has 3 consecutive ones. So if we switch the last two columns, so we're going to get configuration like this. And then we look at the bottom left corner, we are going to have an area 4, right? So that's the interpretation for these two examples. So similarly, you can do for example 3. So here the main constraint is that the total number of elements in the matrix is bounded above by 10 to the power 5. So basically, this number is a decent large number. We need to think of term complexity. So with that said, we can look at the algorithm. So I guess for this problem, if we do it just manually or do a screening by human, so it's very simple to get the area. But the thing is to transform or code the intuition. So the main point, as we mentioned, is to count the area strategically, right? So the algorithm is the following. First, so we want to find for each column the number of consecutive ones ending at a certain position. So this is the first step in the algorithm. That is, for a position in each column, we want to get how many consecutive ones ending at that position. So this is obviously a simple DP, right? So given a position RC, that is the column C, right? Then if the current element at RC is 1, right? Then the dpRC will be dpr minus 1C, meaning that we add the current 1 at this position. So if the matrix element at this position is 0, then dpRC would be 0, because the number of consecutive ones in that position will be 0. So once we get the DP table, we can do the counting and updating the area. So here we can do sorting from high to low for each row. So notice that the order is crucial for the counting. So this part, actually, we can first do coding and then come back to explain more vividly. So in real coding, we could embed the second part in the first part. So with that said, let's look at the coding, and then we are going to explain this part. So we are going to do sorting from high to low for each row, all right? So first, let's get the number of rows, number of columns, and we set the answer to be 0, right? So length, the matrix, and the first row equals the length of the columns. Then we get set the answer to be 0 at the very beginning. Then first we finish this part, right? So this is very straightforward. So for I in range M, right? So what we are going to do is, so for J in range N, right? So if the current element and ij, so you can map the ij to be RC, right? The same thing. So if the current element is not 0, In other words, it's 1, and I is greater than 0. So we can write like this. Is more specific, right? The I is greater than 0, right? So what we are going to do is we're going to do matrix I J equals 1 plus matrix I minus 1J. So in other words, we do these operations in place. So then once a row is done, so we can find the largest matrix ending at ij, right? Submatrix size. So this actually we can do for k, this is the index, for x in enumerate. So we can sort matrix I. So enumerate sorted matrix at the index I. So here we use reverse, right? So reverse is true. But we start from 1. So here we are using this index k starting from 1. So you will see what's the meaning. So then the answer is updated like this: the max, the previous state, and then x is the number of consecutive ones ending at this position in the corresponding column. So we're going to get k times this x. Then we are going to return the result afterwards. So this is the full solution. I guess the point left is this, the explanation for this for block. But before we do that, let me first test this code. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the generic cases. So now let's come back to this one. So first, let's use the first example to do a walkthrough, right? So basically, then you can understand this for block. So then, if we do this one, so the first row is 0, 0, 1, right? So here we have 1, also we have 1, and then this one, because this is a 1 and the previous we have another 1, so the number of consecutive ones ending here at this column will be 2. So now let's look at this one. So the third row, so because this is the 1, and then we can do 2, right? So this 1 plus the last row, and then we have, because this is 0, we do not do, right? So then we have 3, right? Because this is the 1, and then the number of ones, consecutive ones ending at this position is 2 plus 1. So we have this one. Then at each position, we want to do this counting. So we sort the rows, do this one. For example, this one, if we sort the rows, we get 1, 0, 0. So in other words, at this row, at each, because if it ending at 0, there's not a valid submatrix, then we consider the 1 ending at here. So this is just one block. So then it gives a maximum area 1, right? So if we look at this one, so if we sort it, we are going to get 2, 1, 1. So if you look at this one, because this one, the number of consecutive ones, and here is 2, right? Then because this index is, if we use 1 indexing, is 1, so we have 2. So this matrix corresponds to 2. So here you see it's corresponding to this part, right? Then we look at this position. So this position is the second element in this row after we do the sorting. And this one, the number of consecutive ones at this position in this corresponding row is 1. But because this one is larger than 1, because we are sorting in a decreasing order, so it means that all the previous rows, rows corresponding to columns have more consecutive ones. In other words, we at least have a matrix has height 1 and length 2. This gives us, so here, this gives us the area 2 for this element. This 1 gives another element that is 2. So if we look at this one, the 1 here, it's because we are sorting in the decreasing order. It means that all the previous elements corresponding to columns have 1 or more consecutive ones ending at this row. So this way we have at least 3 times 1. So the area is 3, right? So this row actually gives largest column 3. So now if we look at the third row, right? So we're going to have 3, 2, 0. So first, let's understand if we any at 0, for sure, the corresponding area should be 0, right? So if we look at the first element, which is 3, it means that we have an area, it's this 3 times 1. It's corresponding to this one, right? This last column. And then if you look at the 2, so this is the main point. So it means that in this row, all the previous rows have more or equal, more than 2 or equal to 2 consecutive ones. Therefore, so at this position, it gives us at least, because this is the second element, if we use one indexing, 2 times the smaller one, that is 2. So 2 times 2, that is 4, right? So this gives area of 4. So the last one, because it's 0, it gives 0. So overall, the largest one is 4, right? So the return for this one is also 4. So this is example 1. So now let's look at example 2, right? Example 3. So we have 1, 1, 0, 0, 1, 0, 1. So now if you look at the DP matrix, right? So we get 1, 1, 0. So now if we have a 2, right? Because this is any and 1, so above is 1. So here is 0, so we just have a 0. Here is 1, we just have 1. And then we look at the first row. It's already in sorted order, right? So this one, because it's the first one, it has least area 1, right? So this one, because all the previous one is larger, no less than this one. So we have, this is the second element. We have at least an area that is 1 times 2. So for this 0 corresponding to area 0. Now let's look at the second row, right? So here we have, let's first sort it. So it's 2, 1, 0. Then this element corresponding to, because this first after sort, it gives us an area that is 1 times 2. So 1 times 2. So this one, so because this is the second element, all the previous one has greater than or equal to 1. It means that we have an height 1 and length 2 area. So this is 0, so we get 0. So overall, so this largest one is 2. This row, largest one is also 2. So the return will be 2. So now let's look at the code again. So first I get all this in and answer initial state, right? This is very trivial. And then for this double for loop, we're going to set down the DP table. But I don't need to finish setting the DP table to look at each row. So once a row is set, I can look at this, check this each row, the contribution to the final, or update the answer state. So here, for this index x, after we sort reversely, so as we mentioned, the reverse sorting, or sorting from high to low is crucial. And also we start from 1. So because at each position, as like here, so we sort from high to low. At this position, all the previous number is larger than this 2. It representing that. So the corresponding columns has a more, at least equal consecutive ones. Therefore, at this position 2, the corresponding area is the height, that is 2. The length will be the number elements, that is 2, right? 2 times 2, that's 4. So that's the understanding for this part. So with that said, basically that's about it for this specific problem. So here the main point, as we emphasized at the very beginning, is how to count the area strategically, right? So so the overall algorithm is a combination of the idea of DP and the sorting, but the sorting order is very crucial for conveniently counting the area or updating the area. So with that said, that's basically about it for this video. You're welcome to comment or share more thoughts on this kind of problem in the comment. So if you like our, if you like to practice more problems, you can follow up our channel or look at the different playlists within the channel. Thank you.